Good morning. We're going to start today with a talk by Gordana Dodic-Čerković, and she will tell us how every cell processes information and makes sense of it.
Thank you very much. Thank you very much to Oron and Nir for inviting me to this very interesting, exciting event. I'm happy to be at least able to be with you on distance. And conference this far was really enriching and broadening my understanding of computation. And I hope that I have something to contribute with my take on it. So some years ago, together with my late colleague, Mark Bergin, we made the taxonomy of computation. And I have it as appendix to this talk. And this talk will be is already on my webpage. So under presentation, you can find all the slides already. So the introduction, every cell processes information or computes and makes sense of it. So there is some semantics in the whole picture. So cognitive semantics information processing beyond the Turing model of computation. And I have been inspired by your work on Turing machine and beyond the Turing machine. And I have been thinking a lot about possible development of computing. So we can think about computing as it is now or as it was in the past. And we can also think about the future of computing. And my main focus is on the future. And even thinking about applications, historically, we have been using computing, intense computing for calculating different physical trajectories or in astronomy or for war technology and so on. And today we are computing much more in a cognitive field. So we are thinking about intelligent computing, also computing used in biology in the first place and medicine. So the application fields are different. The focus of applications fields is different today. So it is normal in every science, we are developing models. In physics, we were moving from classical physics, broadening the domains and the approaches to relativistic Einstein's physics and so on. So it's a normal process of development of every research field that we are learning more and involving more. That's the ambition for the future. So that's the perspective of my talk today. And I don't know how many, I know many of you, but maybe I should say that my name is Gordana Dodic-Čerković. I'm coming from Chalmers University of Technology in Gothenburg, Sweden, and Mälardalen University in Västerås. So I have two affiliations. And my webpage is given here. Is very simple, Gordana SE. So okay. So my background, just to understand where I'm coming from. I started as a physicist in quantum physics and theoretical quantum physics. So working on a very formalized languages and very mathematically based. And then I moved towards computer science. I made my second PhD in computing and philosophy, actually. My opponent was Luciano Floridi. And from that time, my defense, I learned that my approach have some major problems. And one of those problems is that I was supposing that the nature, that we can make a model of computation which would cover all the natural processes that exist. And his line of criticism against this approach was that it is too general and that everything is getting like a gray goo, nothing can be distinguished, and so on and so forth. So after 2006, I was trying to build defense for this approach, where we try to translate very simple. Actually, the idea is very, very simple, that we express whatever we know in physics and other sciences, express in terms of information and computation. So that's the main point. And how to make it so that it is not trivial, I will try to explain. And my most recent interest is in morphological computing and cognition. I was moving towards cognition more and more, and trying also to apply computational models to cognition. So, and broadening ideas of both computation and cognition. So this is the quote from Ilya Prigozhin. I invite readers not on a visit to an archaeological museum, but rather on an adventure in science in making. And it is really in making. There are a lot of gaps and holes, and this is a puzzle that I'm trying to collect and understand a bigger picture from what exists. And this is from Leonard Adleman. Biology and computer science, life and computation are related. I am confident that at their interface, great discoveries await those who seek them. So very often people imagine life and computation as something completely opposed to each other. But we will see how we can get them together. And before I started this presentation, I wrote to GPT-4 asking, what does it mean? What does it think about the title, Computing and Making Sense? Our metaphors should, and I have got the answer. In short, GPT-4 says that it is an interesting idea, but compute and make sense are metaphors, and I should say meaningfully process information instead of making sense. And I should not say compute when I talk about the cell. And I will explain how I was meaning. And of course, the use of the word compute and making sense in the title is not conventional one. But I will try to defend the use of those words. So I'm claiming that every cell processes information, computes, and makes sense of it. And the framework is information, computation, and cognition. Three main ideas or notions I'm using to try to understand natural processes in terms of computation. And they are connected. And I'm using this metaphor from Gödel, Escher, Bach by Hofstadter, where you see that you have, for him, the three notions were the three persons, but for me, the three basic things are information, computation, and cognition. And one thing that I should make clear as well is that the underlying principle is observer relativity and agency. So the basic building blocks are active, they are agents. Unlike many models that consider their basic building blocks as passive, like a stone or such materials, this is assuming in general that the basic building blocks are active. And this observer relativity is very well expressed by Maturana and Varela, who said that everything said is said by an observer to an observer. It could be oneself, but also other observers. And I never understood actually why people have problems with relativity. I think relativity is such a normal idea. And for example, in theory of relativity, it doesn't mean that it is subjective. Being relative is just being measured with respect to some origin that you choose. Instead of taking some absolute origin or some absolute measure, you have some defined relative origin or measure. So relativity is normal in sciences. It is used. And observer dependence, it is normal for relativity theory. It's normal in quantum mechanics. It's normal when we think about complex system. So it has such a complex structure that it is normally dependent on the point of view where which you take and describe the system. So I will tell you the argument in short. So basic assumption is we are part of computing nature that consists of informational structures with computational processes. Everything that happens in nature, all the processes can be expressed in terms of computation. And we have heard the other day that there are some processes, some people are claiming, which are computational, clearly, like our immune system. It's a computational system. But our metabolism or digestion or guts cannot be explained in terms of computation. And I would say that it really, what we take for computation, what we define, is dependent on what we want it to do for us. And now we can also explain metabolism or whatever biological process with help of computation. So the other claim is that information is a structure consisting of differences in one system that cause differences in another system. How do we perceive this information from the environment? We take data, and it is also relative to our structure. So we have structure in the world and our own inner structures which interact, producing this information for us. Computation is information processing and dynamics of information. It is a physical process of morphological change. I'm using this term morphological to mean both the form and the structure of the material in the informational structure, which is the physical implementation of information, as there is no information without physical implementation. So all information that we have is physically implemented. Both information and computation appear on a succession of levels of organization, abstraction, or resolution, or granularity of matter energy in space-time, in nature. So when we study nature with the instrument of different sciences, we will find physics and chemistry and biology and so on. So that's how we can understand what is happening in nature, and on each of those levels we can define computation. Of all agents, which I defined as entities capable of acting on their own behalf. So that's the definition that Stuart Kauffman and Teres Deacon are using. So that they are entities which are acting on their own behalf. Only living agents have the ability to actively make choices so as to increase the probability of their own continuing existence. This ability of living agents to act autonomously on their own behalf is based on the use of energy and information from the environment. Cognition consists of all infocomputational processes necessary to keep a living agent's organization integrity on all different levels of existence. So cognition equals to computation of information or infocomputation. In living beings, cognition is equivalent to the process of life, and that is something that Maturana and Varela already has been studying in 80s, and Stewart in 96 has a paper on titled "Cognition is equal to life." So processes of cognition are processes of life. The complexification is a result of physical or morphological computations in those living systems. Every cell processes information or computes and makes sense of it, goal-directedly. Gut cells compute individually and collectively as a tissue, organ, and a part of an organism. And I refer here to the article of Manica and Levin, modeling somatic computation. And they have been studying the differences between somatic cells, ordinary bodily cells, and cells in the nervous system. And they are showing that there is no principal difference in mechanisms. You have gap junctures and calcium channels and all those processes that we find in neurons, we find in somatic cells as well. And they claim, they show how those mechanisms really work in practice. So I refer a lot to research of Michael Levin and his lab, because they really show how those processes of information in living cells or in living organisms work. So the next step is evolution. I use the extended evolutionary synthesis when I think about the evolution of those biological systems, and evolution also as a computational mechanism, which considers that not only random mutations, but also sequences of changes caused by laws of physics and chemistry, described as morphological computing, lead to the development of new structures which are exposed to natural selection. So Jablonka and Lamb and Ginsburg and Jablonka and Noble and many others have been describing those processes where the agents, the living cells have their own preferences and goals and make sense of information from the environment. And that's the basis for evolution. That's not only statistical variation that plays through. Cognition, intelligence, and similar capacities of physical and biological systems come in degrees. And that's also very important, because many people make this simplification like you are cognitive or not, and there is nothing in between. We had also, I think Dimitri was thinking about artificial system. Can we say that the large language models have cognition? And if you think in terms of degrees, and for example, Levin has been writing quite a lot about how all those things come in degrees. So we can ascribe certain degree of intelligence or certain degree of cognition to even to artificial agents. I will come to this topic when I talk about cognition. One thing that is happening, so I'm trying to update all those notions as they come in research fields. So this is the new result, which says that we should revise a central dogma, and we need it for understanding of biology. And this is a very new article, Revised Central Dogma for the 21st Century. All biology is cognitive information processing. So they say that's Miller and Balushka and Reber and yeah. So they are talking about the necessity for taking into account that not only DNA, but also the agency of cells, their ability to process information and to act meaningfully in terms of their own goals, those are the basis for for evolution. So they say all biology is cognitive information processing. So that's one of the arguments in that direction, how to understand living systems as the whole, from the single cell to the organism to the ecologies and everything. It's all goal directed. It's all agency based information processing or computation. So I have those three basic ideas. So those are information, computation, and cognition. And I have to hurry because I have many slides. So I will actually not explain those basic terms. I will go very quickly because I have so many things to tell you. Information is taken to be a fabric of reality for an agent, and even Luciano Floridi has this informational realism in which he says that the whole of the universe is informational structure. So it's not much far away from the idea that this informational structure has dynamics, which is computation. So those are the claims where I take inspiration from Floridi and Sayre, that reality consists of informational structures organized on different levels of abstraction. And remember, I'm always looking from the point of view of an agent. It is agent-based or observer-based ontology and epistemology. So the relational definition of information is the classical one from Bateson, and then you can go into the details and then criticize Bateson as Aaron Sloman did, but I will not go to that level of detail. There is, in physics, of course, there are those basic approaches, it from bit, by Wheeler. Which explain how our understanding of the world is a result of information processing. That there is some information coming to us through levels of computation that we observe or understand or make sense as a reality for us. So whatever we have as a notion of real object or real world, it is the result of information processes. And Wheeler is not, of course, the only person who discovered this connection. People who today work, for example, Stephen Wolfram, he published a newly project to find the fundamental theory of physics, which is basically this physics from information. Carlo Rovelli as well, he developed this relational quantum mechanics, also explaining the mechanisms based on information processing. Computation, I mentioned many times, and here we talk about a structure as information and process as computation, or being as information and becoming as computation. And this is the explanation of the idea of computing nature. Reality is an informational structure with computational dynamics. And I just want to mention one model which connects directly to indeterminacy of computation, and that is Hewitt's actor model, which is the basic theoretical model explaining computation in terms of actually in parallel with the explanations from physics. Unlike Turing, who was thinking in terms of logic and logical machines, Hewitt thinks in terms of physical objects. So he has actors which exchange messages in between. And those actors, they are often in a state which is not well defined because the messages are traveling in between. So for him, the normal state is that you don't have the updated system and you don't have a current state of the system in every moment. So for him, the indeterminacy is inherent to this system. So, and those are the details. There is a parallel to the ideas from physics, where physical elementary particles exchange other elementary particles and in that way interact with each other. So it's basically thought as a physical idea. So the idea of Turing as a logical approach to computation has been questioned by many and on different grounds. Also Jack and Diana and many others thinking from different points of view and discovering that there is a world outside the world of Turing computing. There are other possibilities to compute in other ways and for other purposes as well. So Peter Wegner was thinking in terms of interaction, the main point in interaction. Mark Burgin, he tried to approach this with a more general definition of algorithm. We have heard Dershowitz and others have been thinking about how to define the algorithms Turing has been thinking about, so that the idea of algorithm was evolving as well since the time of Turing. So more general definition of algorithm. Yuri Gurevich has written a very interesting article, Unconstrained Church Turing thesis cannot possibly be true unconstrained. So we need to know how to what are the implicit constraints for Church Turing thesis, and what happens if we relax those constraints, if we take some other constraints. Barry Cooper, a Turing machine does not cover higher order of computation, and that was also written by Mark Burgin in some of his work and in some of our common work. Samson Abramsky, he puts the focus on computing as a behavior. And that's very important, because we are really more and more using computing for producing behavior and interpreting the behavior. So this is Gurevich. And the third term is cognition. So this is the classical dictionary definition, and here are the components. So if we want to think about, can we say that the cell is cognitive system? We can search if it fulfills those conditions. If it has perception, attention, memory, language, problem solving, and decision making, and executive functions. And we can see people have been writing about this and studying, especially unicellular organisms. They observe perception, attention like a focus, memory, language. Like in bacteria, they have been studying quorum sensing, and those cells are using either parts of DNA or other molecules to exchange within each other, and they exchange information in that way. So they have some sort of language. They have, of course, problem solving and decision making. And about executive functions, it is a question if they have any. But we can say that if we accept that cognition comes in degrees, we can say that those single cell organisms have almost all of those components, not all, but some of them, interpreted on their own level of existence. So life, as I mentioned, can be seen as a cognitive process, and autopoiesis as a self-reflective process. I have mentioned it, and here is a lot of work, just to mention, about this fundamental basal or minimal cognition on the cell level, where people, biologists and other people from computing have been studying what cells are doing and how they behave and so on, and based on that made conclusions about the cell cognitions. cell cognition. So work of Eshel Ben Jacob as well, even as early as 2006, studied bacterial know-how and their cognitive behaviors. So that there is information processing going on on that level, and the mechanisms have been studied. And for example, Friston, Levin, and others studied a relationship of the single cell with the environment. What is happening with this boundary between one organism and the others, or the rest of the world. Those are the things that people already know how to model and how to interpret. So, and then in studies of Levin, for example, there is this step from the cell, from one cell to multicellular organisms, and how the whole process of creation of multicellularity can be described and understood. And they talk about cognitive light cone of a single or of any biological system. So Levin would say that the single cell have a very small world, and that's similar to the Umwelt idea that the cognitive world of an organism is dependent on what kind of organism it is, which sorts of information exchange with the environment, and so on. So we are now in search of adequate model of computation capable of implementing information dynamics in cognitive systems, including such biological systems. So as I mentioned already, cognition comes in degrees, and we are trying to see how we can approach those natural processes beyond the logical computing, if we can integrate the knowledge from other sciences like physics and chemistry and biology and so on. So this is the idea of computing nature, which some people call pan-computationalism. And there is also nature-inspired computation. And I here refer to very nice work in natural computing. This was communication of ACM, and the article is the many facets of natural computing by Rosenberg and Kari. And here are other systems that you can understand as computational in nature. So they are the pictures from the elementary particles up to bacteria and many cellular organisms. And one of the basic notions here is interaction, and this interaction can be modeled as a network. So we are using understanding from science, from model-based science. And if we think of in terms of computational aspects of model-based reasoning, we can describe information and computation as conceptual networks. So we thinking in our discussion about what is computation, what is information, is computation has computation some properties or not, we should keep in mind that we are all parts of those networks, and some of us come from some different connections, have different contexts for them. So it's no wonder that we see different pictures. But having in mind that those concepts are developing all the time, they are evolving with our increased understanding of the world. And I had a discussion with Marcin Miłkowski, this year about the relationship between computation, information, cognition, and their embodiment. And we have been discussing meaningfulness of introducing this computing nature in general, or pan-computationalism, and the weak sides and the strong sides, and so on. So as I said several times, we have this, or I have this idea of structure and process, or being and becoming, as a parallel of space-time and matter-energy. So when we say computation, it couldn't be a natural kind, or it's too broad to be applied to any process. I think we can see it in parallel with those notions of structure being space-time, or process becoming matter-energy. Okay. There are different models of cells. I will not go into details how this cognitive ability of organism is implemented. And if you wish, you can see the cell as a classical computational system with inputs, then information processing and outputs. But as we have heard several times, it's not necessary to have inputs and outputs because of interactions of the parts of the system. System is evolving. This is the comment on mechanicity of the cell. This is also a cell with flagella, and if you look at those parts, they look like extremely mechanistic. So sometimes we like to imagine that life is so very different from mechanism, but probably on those very fundamental levels we find a lot of purely mechanistic explanations. And I don't know if you have ever seen this creature. This is single-celled Lacrimeria olor, single-celled organism, which is a predator, and it is all the time searching for food and eating. So it is sort of an automaton with two states: search for food, eat it. And it's an enormously fascinating how effective it is. It has no nervous system, no control system that we can see, but it has a body, neck, and a mouth. This single cell, which opens when it swallows some other cell or some food. So it is extremely effective, and we don't understand at all how it works, but probably on some basic mechanisms coming from chemistry and physics. So that's just illustration. I will not have time for discussion if I don't hurry. Basal cognition. So that's the cognition of the cells. There are two special issues of Royal Society Biological Sciences, which are addressing this, and of course they are open access, so, and extremely interesting.
5 more minutes.
5 more minutes, okay. So I go very quickly, just to mention that there are studies showing cognition in plants, animal cognition, of course, on different model organisms, and computational studies of information processing in brain and nervous system. So Turing himself was thinking about what comes as a next step, and he as we have heard, described the morphogenesis, and that is kind of morphological computing. Here is the illustration of those interactive networks on different levels of organization, from single cells up to. So the question, just to quickly summarize, in what sense can we say that guts compute, or stomachs, or whatever, somatic cells? In the computing universe, guts naturally compute. That's the first answer. But here is how. On microscopic level, the gut does have a complex system of nerves and neurotransmitters that communicate with the brain, known as a gut-brain axis. This system helps regulate many processes in the body. The communication network is so intricate and important that it is sometimes referred to as body's second brain. And so on and so forth. So that's one picture. On the microscopic level, there is also growing evidence that the bacteria in our gut, the gut microbiota, can influence our brain and our behavior, including mood and mental health. So this is bi-directional communication between the gut and the brain, and so on and so forth. So, and of course, we have a gut feeling, and that's not without reason, this expression. I mean, if every cell computes, then the whole organism and with all its parts computes. And I will conclude, before I show you the appendixes very quickly, I will conclude, this is a conclusion. And using Lila Kari and Gregor Rosenberg quote from this article, The Many Facets of Natural Computing. They say, in these times brimming with excitement, our task is nothing less than to discover a new, broader notion of computation, and to understand the world around us in terms of information processes. So this is the program for computer science that they are announcing. Let us step up to this challenge. Let us befriend us fellow the biologists, our fellow the chemist, our fellow the physicist, and our fellow the philosopher, and let us together explore this new world. Let us, as computers in the future will, embrace uncertainty. Let us dare to ask afresh, what is computation? What is complexity? What are the axioms that define life? Let us relax our hardened ways of thinking, and with deference to our scientific forebears, let us begin anew. So if Turing would be alive today, I'm sure he would start anew. So I think their message is really something that appeals to me. So that was my basic idea, and I provide some references and acknowledge this Swedish Research Council, which supported my research. And here are the supplementary materials. So books that I'm using to and coming back to when thinking of this. So there are many really extremely good. This is number of books in terms of natural philosophy. So trying to approach this complete picture of nature in terms of information computation, learning more about how people are thinking about nature in general, natural philosophy. And here are the books that inspired me in dialogues with my colleagues. And I was really extremely thankful to Ron for inviting me to participate in the discussion of his book. Here is the article on taxonomy of computation, just to see how many different ways to look at the computation exist. And Paula mentioned that we are not mentioning domain, and here is the division even with respect of domain. So representational domain, database taxonomy, operational taxonomy, process-oriented taxonomy, level-based, spatial, and so on and so forth. So, and people have been, as I mentioned, talking, yeah. So that's the rest of the materials I was using in preparation of this presentation. Thank you very much.
Very much, thank you. We have almost 15 minutes for questions.
You hear me?
Yes.
Okay. Thank you for this very comprehensive talk, and I just wanted to know a bit more about the notion of information that you use, whether it's something that is just a causal process in a complex system, or is there something more to that? And if yes, whether the something more is something that is metaphorical or some other thing, and especially how do you think the relation? What do you think about the relation between information and representation? Especially, do you see in what you review also, they talk about misinformation, so there is some norms. So maybe you could say a bit more about this.
Yes. That's a great question, because you find all of this actually basically in the picture of information. So the idea is that we talk about both the agent and the world, and the agent could have information which is about intrinsic structures that it has. So if I share my screen again, I can show this part which is about information. Let's see if I can see my presentation as well. But maybe I can tell you, am I sharing or am I not?
Yeah,
Okay, that's the part of the presentation which talks about information, and information is defined as a difference that in one system that make a difference in another system. So from the point of view of an observer, it could be a single cell or it could be a human. This information could be a photon coming from the universe telling us something about the star or whatever, going through different transformations coming to us. So all the time through different systems for which it made the difference in different ways. And in the end, let's say it is an astronomer looking in the telescope. In the end, the information will, or the photon will hit the retina, and we will get this signal. In the end, it will be a business within the brain, making connections with this input that we get right now, with whatever we have as a memory, with the association with other events that we already know about, and so on. And in the end, we will have an interpretation of whatever we are seeing. So there is a causal process, of course, from the beginning to the end, like in any scientific theory, which explains how those processes are going on and what is happening. Whatever we know about the nature of natural processes should be a part of this computational picture or information processing picture.
Corey.
Hi, Gordana. I'm Corey Maley. We haven't met. So at the beginning of the talk, you mentioned that, well, let me echo Oran. I think this was a really interesting, comprehensive view of different ways we might think about computation. And insofar as you're using it metaphorically, I think this kind of approach can be really useful for, oh, sorry, camera's over there. Sorry, that's confusing. There's two screens. Hi, I'm Corey. Now you can see my face. So these metaphorical approaches, I think, can be really useful for generating different ideas and things like that. My own interest is in taking computation literally, and I mean, maybe this is just not something you're interested in, but my concern would be if we tried to take some of the various ideas that you have literally then there is a kind of rampant pan computationalism, and just every physical system will be computing somehow or another. And it sort of, the way I understand, I mean, you mentioned a lot of different kinds of computation. And then it seems, maybe some of this wouldn't apply to some of your notions, but then it seems like what computation will be sort of synonymous with kind of an abstract, discrete state kinematics, like how different states change, but without respect to particular forces or causes, just kind of in an abstract way. And I guess I'm wondering, you know, like I said, metaphorically, that might be a really useful way to think of, you know, lots of different ideas. But it seems like taking it literally, computation is not anything different than what I said, just kind of the abstract kinematics of abstract spaces. So I was just wondering if you, am I totally wrong about that? Or
I didn't have time to tell more about other models of computation, especially those which are presented in the Handbook of Natural Computing by Rosenberg and others, where they use specific systems and describe them in terms of specific computations. My ambition was to connect to the content of the workshop, but you have membrane computing, you have reservoir computing. Those are concrete things, so you have an idea of computing. Either the material performing some processes for you and you read the inputs and outputs or whatever, or you model in terms of some continuous or discrete model what is happening in the world. So maybe this picture of Hewitt is misleading, because he has like elementary particle exchanging other elementary particles, so one would believe that it is discrete, but it is not. It is both. It could, in case of discrete systems, physical systems, be discrete or continuum as well. So we can have reasons to model something as a continuum. So there is no assumption about the discreteness of the system. Just in parallel with anything that happens in physics, you have some of physics of continuum, which is better treated as continuum, even though you have approximations in discrete.
Great, and we have 4 questions and 6 minutes, so let's try to keep everything as concise as possible. And
Hello again, Gordana.
Thanks for the talk. So first of all, a quick comment. You mentioned before that Luciano was an opponent in your early work and having exposed some significant problems with your framework. So I'm not familiar with that framework, but I can say in your defense that in Luciano's framework, especially when we talk about informational realism, there are quite a few holes. So I wouldn't be too quick to give up your framework. But more seriously, so when we talk, and maybe a follow-up to Corey's question, so whether we talk about metabolism or bacteria and single-cell organisms, you showed some criteria that need to be met in order to describe it as cognitive or whatnot. So I guess if you can say a bit more about what would be language or language processing in those cases, it would be useful, I think, because you mentioned something about exchanging or processing symbols, and I'm not quite sure what might qualify as a symbol in the case of either the stomach or definitely a single state or single cell organisms.
Okay, that's a good question, because I've heard an interview by Michael Levin, who said everything is covered, but not the language. And I think language as well, because, for example, Bonnie Bassler, she has been working on bacterial language for many years. And she has detailed descriptions on the chemical level. That's the chemical language. On the chemical level, what is exactly happening and how bacteria learn from each other and how they organize in films or swarms, given the input from the environment. So their symbols are chemical molecules that they exchange, and they make sense of them in that way that they integrate them in their metabolism or in their own DNA or whatever. They make changes, adjusting accordingly when they get the message from the other bacteria. So they like do voting based on if the swarm says it's a too acidic environment, they have some threshold, and everybody then if enough of bacteria says it's too high, everybody will react on that information and behave accordingly. So she is describing this as a language, and I can send you the references. And I think it is a language. If you generalize the idea of language, it is exchange of messages. It doesn't play any role if it is the object. We have also a possibility to communicate exchanging objects, physical objects. And those bacteria, they communicate exchanging chemical molecules. That's the short story.
Okay, thank you. Paula?
Yeah, hey Gordana, thank you so much. So I have a question about the importance of the observer, right? Because you said at the very beginning, you were very explicit about the necessity of someone being there and interpreting, right? And then, like, I know very little about natural computing, but it seems that it cannot stay uninterpreted, right? So the whole burden of deciding whether something is computation or what is being computed is actually being delegated to the observer, right? So I go there and I see all those, wonderful organisms, and then I'm there and I say, oh, I can make it, I can translate it into the language of computing, right? So could you say something more about it? About how it works and what is this importance, and what would happen if we would just leave the universe without our intervention and interpretation of necessity?
Thank you, Paula, for this great question. Yes, that's exactly what you say, that comes to our own interpretation of what we want computing to do for us and what we want to interpret as a computing. And I recommend interviews or lectures by Michael Levin. There are many on the web, and he explains, he is into the field between computing and robotics, and he biology and robotics, and he is thinking in terms of combinations between biological and computational systems. And people in medicine are already using these nanotechnologies for many purposes, for monitoring the body or as a medicine and so on. So we will see more and more of medicine relying on different computational methods and different computational devices. And getting this smooth connection between the device and the biological body is a very important approach. One thing that I should have mentioned about the article about natural computing and this programmatic Rosenberg-Kari paper is that they say the main point is in learning. So we are learning in both directions. If we say that, okay, this is the natural computing going on, and I'm studying a biological system. I learn from biological system what could be computed, and then when I develop my computing, I can go back to the biological system and find more or find the differences, and that's they say that is the learning process that is the most important. And I think in the whole development, even now, when we develop those large language models, we are going back to human brain and trying to understand the parallels, the neural networks being on the level of system 1, Kahneman, and what we are missing, we believe we are missing system 2. Those are the higher levels of cognition that we have as a human beings that large language models still don't have, symbol processing and such things. So we have this possibility, having in mind the computational picture of something, let's say intelligence cognition. We go back to the biology and learn.
Yeah, so maybe we can squeeze in one last very quick question because we're already behind schedule, and then.
Okay, Tecumseh Fitch, we're studying language evolution and I'm a cognitive biologist, and I'm very sympathetic to your viewpoint and I've written on it myself. But I think all of the questions are getting at what I see as a central problem, which is we're expanding these words, computation, cognition, symbol, language, beyond their normal bounds. And as someone who's very interested in understanding animal computation as done by brains or language as done by humans, the worry is that there's too many bridges or too many levels between this, say, single cell computation or cognition, if you want, and brains. And the model doesn't seem to leave space for the specificity of neurons or of units of neurons and or language. And so do you see any dividing lines, or is this just one great continuum?
I think what I see in the whole approach is learning from sciences, or learning from whatever we know in other domains, translating in terms of computation and trying to construct mechanisms and models that would smoothly connect to the natural world and help us explore more, understand more, or intervene more, or change, or whatever we want.
Thank you. So thank you very much. Thank you, Gordana.
Thank you. Thank you.
Okay. Great. So thanks so much for having me. This has been a really stimulating conference workshop so far. In fact, so stimulating that I decided to completely rewrite my talk last night in light of things that I already wanted to say and things that people got me thinking. So I don't know how well this talk will go. It might be a little disjointed. Hopefully it'll be sort of interesting. The radical part of rethinking computation is in the kind of literal sense of, radical from the Latin radix, meaning like the root, right? And so the point of this talk is to kind of hopefully make some people think about what computation is from a different angle, and in a literal sense of computation, not a metaphorical sense. So this is sort of a nice pairing with the talk that we just saw. Okay, I think this clicker will work. This is a nice quotation that I found. Some of you may know that most of my research in computation has to do with analog computation and me trying to explain and clarify that the simple analog digital dichotomy, where analog means continuous, digital means discrete, that does not do the job, just based on some conceptual kind of thought experiments that David Lewis had back in the 70s. But if you really look at the analog computers from the early 20th century, there were discrete analog computers that were not digital. Right? I could talk more about that in some detail. But anyway, this quotation, because digital computers and computation have been so successful, they've influenced how we think about computers as machines and computation as a process. So much so, it is difficult today to reconstruct what analog computing was all about. I think that's true. And I think you can generalize from this to say it's hard to reconstruct what computing was all about. So I'm going to be maybe more provocative than I mean to be, just because that helps grab people's attention and gets them excited and then they want to say things. So, I do believe these things, but I like to be provocative. So I think that we've all been fundamentally mistaken about the nature of computation itself, okay? We've been too concerned about one mathematical model of computation and not computation itself. And I think that we should take a step back and remind ourselves what computation is in the light of what it has always been about, right? So say more about what that means. And this is another element of the mistake I think we made. We need to understand computation on its own terms. Before we import ideas from, say, the philosophy of mind, like content and things like that, we have to understand computation simpliciter. Then we can be in a position to know whether computation can do the jobs that we've assumed that it can, right? So there are lots of examples of, Rodana mentioned some things. There are people who want to implement computation in slime molds, and there's quantum computation. There's all these things, right? And if you want to be metaphorical and just think, oh, this might be an interesting way to get some ideas, great. I'm interested in whether those things can literally be computation in some sense that makes computation interesting in a way that's not just something else, synonymous with, like I said before, kinematics or something like that. Okay. What's going on here? Since the dawn of time, people have wanted to do things with numbers, right? Sometimes practical things, like you want to know how much grain you have or the area of your house or whatever. Sometimes theoretical things like properties of prime numbers or things like that, right? There's a big problem with this enterprise. Numbers are abstract. Well, if you don't like abstract objects, they don't exist at all, right? In either case, you have a problem. How are you going to do something with abstract or non-existent things? Well, the solution is easy. Just physically represent the numbers and then manipulate those representations, right? Now, this talk is about to end. The manipulation of physical representations, I think, is the essence of computation. There might be more ways of extending computation beyond that, but that's the core. And I'm just going to sort of gesture at why we should take this seriously. This is, like a book length or maybe multi-book length project to really defend it, but I just want to get everyone mad at me and alienate you all so that, we can make each other think. Okay, so like I said, my work has been on this comparing and contrasting analog representation and computation. This is just a cool picture that I like from this Nuts and Bolts magazine. But I think the analog digital distinction roughly gets at two fundamentally different ways to represent numbers that we've been doing for millennia, right? These two different ways, they almost correspond to analog and digital representation. But for now, I'm just going to say we can represent numbers by their name or by their magnitude. Whatever numbers are, these abstract things or whatever fictions, we can represent them by their name or by their magnitude. So let's talk about names first. Consider the real number pi. One name for it is, laser pointer. That thing up there, that word. Another name for it is this, right? That Greek letter. Another name for it is this infinite sequence of digits, right? These are just names for these numbers. And the name here is arbitrary, relatively uninformative. You have to know some certain conventions. This kind of name is a little more informative, right? This tells you something about the value of the number. And I like to think of it, and this is not a perfect analogy, but the town where I used to live in Lawrence, Kansas, has these two bakeries that are kind of famous. One is called Wheatfields. The other is called 1900 Barker, right? Those are just names of these places. I have no idea what the address of Wheatfields is. I know the address of 1900 Barker. The address is 1900 Barker, right? So if you know how street names work and how addresses work, this name tells you something much more than this. That one's just arbitrary, right? So there's a way in which these digital representations are more informative than just these arbitrary names, right? But they're just ways of naming numbers. And one really useful thing about this type of representation that we all know is it's amenable to many types of manipulation, right? And I say this is just digital representation. It's what we're all very familiar with, and it's used in all of the computers in this room, right? Except in binary rather than decimal. The number pi can also be represented in a fundamentally different way, by its magnitude. Right? So there's a couple ways you could do, well, there's lots of ways you could do this, but you know, pretend this is a 6 pi meters long. Pretend instead of 1 kilogram, that says pi kilograms, right? So now we're using, you know, pi has, again, who knows what numbers are, but one thing they have is a magnitude. And what we're doing to represent that number is using a physical magnitude, right? And representing a number's magnitude via a physical magnitude is just what analog representation is, right? This slogan is due to Chris Peacock, actually. Now, there's a lot more to say about this to make this precise, but I think, you know, you get the contrast for now. That's the main point. Now, analog representation is also amenable to manipulations, but of very different types. And one of the things that I've tried to convince people to understand is that analog representation is often continuous, but it need not be. It can vary in discrete steps, right? So simple examples, you know, if think of an hourglass, it's an analog representation of elapsed time. If you want to, you know, fill it with liquid and say that's continuous, great. If you want to fill it with particles and say those are discrete particles, great. Doesn't matter. The important thing is you're representing a magnitude by another magnitude, right? Now, I want to give a couple examples of some components of analog computers just to show how very different they are from other types of manipulations. If you've seen a talk that I've given in the last like 4 years, you've seen a couple of these movies already, but you know, bear with me, they're fun. This is a mechanical multiplier from a Navy training video showing how these basic components work. And it's going to go step by step and break them into pieces to show you what's going on. We have inputs A and B along here, and then here's the output. So how this works is there's a fixed thing there, and as A goes up and down, it makes this linkage rotate about that fixed point, right? B slides from left to right, has a sliding pin that's constrained by this groove and that other linkage, so that that pin will move according to where A is and according to where B is, right? So far, so good. It's a rather simple mechanism. That sliding pin then drives the output up and down on the left side. And when the two pins are on top of each other, basically, we can use that as a sort of origin point, which then allows us to add some labels to A and B, which we're about to see here. Yeah, so it's a little fuzzy, but this is 0, +4, -4, 0, +4, -4, and then 0, +15, -15. And as you move the inputs, the output will be the product of the inputs. So 2 times 3 is 6. If you want to talk about that in the Q&A, you can do that. Who knows this? And it just goes through some examples showing you that it actually works. So it's a cool little mechanism. Note how very different this is than an algorithm that you would use to multiply 2 numbers via their digits. Like just a simple algorithm that we all learned in elementary school, right? This doesn't represent numbers by their digits. I mean, it does on the inputs and outputs just for our convenience, but the mechanism is using displacements, right? That's what's used to, or lengths, if you like, to show or to represent the magnitudes of the numbers. And it works for negatives and everything else. A slightly more complicated mechanism, well, sorry, a much simpler mechanism. That previous one is very difficult to describe in written language, like in a paper. This one is much easier to describe. I've actually done it in published work, but it performs a somewhat more arguably complicated mathematical operation of integration. There's going to be some labels on here that were relevant to you if you were in the Navy, but we'll ignore them for now. Let me just tell you how this works. When this is run, this is a turntable that's going to operate, it's going to turn at a constant rate. This is a little linkage that goes back and forth. And these are two steel ball bearings that touch this turntable. And then they drive this roller up here, right? So what happens is you have a function that you want to compute the area under, right? You want to integrate the function. This goes back and forth, basically tracing the height of the function at various points. This is the output. This basically counts the number of rotations. So when it's out here, it's making this roll at a certain rate. As it gets further from the edge or further from the center, this spins much faster, right? As it goes toward the center, this is slowing down. And when it's right at the center, it doesn't move at all, where the function is 0, right? And if it were to go to the right, when the function is negative, then it would unroll, right? Subtracting, which is what you want for integration. So those are just some mechanical analog computer components, really just used to illustrate how different they are from the way digital computers work. Now, I want to talk about Turing machines and computability theory just for a little bit, because one of the mistakes that we've made, like I said, is taking Turing's work way too seriously and asking it to do jobs that it was never meant to do. I'm sure everyone's familiar with Turing, and this is, by the way, this is not a diss on Turing. He's one of my intellectual heroes, right? And famously, you know, he opens his 1936 article saying we may compare man in the process of computing a real number to a machine which is only capable of a finite number of conditions, right? And he was interested in, and I'm sure most people in this room know, this mathematical problem of, you know, originally it was what numbers are computable. The thing that he had in mind were, you know, or inspired him, were these women, right? Well, not all women, but often women that were computers of his day, right? I love this picture because it's the computing division, the computing section is just filled with these women with their adding machines and their notepads, right? That's what the computer room once was, right?
Where is that?
Ah, great question. I can tell you, but not now.
Bletchley Park, let's take a guess.
And you know, he wanted to know what of the real numbers could people like this compute, right? He wanted to answer mathematical problems about that, but of course you can't answer that question or even begin to ask it sensibly without a mathematical model of this process, right? Which is the Turing machine. Most people know that story. Here's another picture I like even more. This is a computer at, the woman is the computer at the NACA, which is the US predecessor of NASA. And she's got her, you know, graph paper with the squares and her adding machine and her slide rule, right? Now, this is an analog device. This is a digital device. She might be performing some digital computations there. It's unclear, but this really is an analog device, right? Now, Turing never intended to analyze analog computation. That was just not what his interest was, right? This is, again, not a diss on Turing. It's not like he, you know, forgot something or messed up. That just wasn't his interest. Right? But analog computation is as legitimate a form of computation as digital. I think it's very hard to argue against this thesis because analog computational mechanisms predate digital mechanisms. And by a lot, right? This is the Antikythera mechanism from about 2,000 years ago. This is the actual pieces. This is a modern reconstruction. People said this may well be one of the first analog computing devices used to compute various motions of celestial bodies and things like that. Amazingly complicated and precise for what we assumed was possible 2,000 years ago, right? And I think analog computation differs from computation in many ways that people have failed to take seriously. Primarily because that original quotation, because digital computation is the thing now, right? So people just kind of poo-poo analog computation. But let me mention a few of the things that I've argued some in print. With analog computation, there's no clear hardware-software distinction, right? I'm just going to mention what these are. I'm not going to argue for them. There's not necessarily algorithms in the same way. There are mechanisms, right? But in that, the ball and disk integrator, that's not using an algorithm the way you would on a digital computer, right? If anyone has done any scientific computing, there's lots of algorithms for integration, like, third order Runge-Kutta algorithms, or something simple like Euclid's algorithm, right? Where you can specify all the steps, right? The mathematical operation is integration. You say, here are the representations, and here's the algorithm we're going to use, right? And then we'll talk about the hardware. In analog computations, there's the mathematical operation is performing, and then there's the mechanism, which is just built into the hardware, right? It's not really an algorithm. If you want to expand what algorithm means to mechanisms, fine, right? But it's clearly something different, right? And analog computers are not implementations of automata. I haven't argued for this in the same way, but you end up with a really strange notion of automata if you say that analog computation or analog computing systems are implementing a mathematical formalism in the same way that digital computing systems are implementing a mathematical formalism. I don't think it's the same. So one of the things is, what's necessary of digital computation, I think this is clear in a lot of ways, maybe not always, but those necessary things of digital computation might not be necessary of computation in general, right? We have an n=1 problem, right? We said, okay, well, digital computation just is computation. So whatever is necessary there is necessary for all computation. And I don't think that's necessarily true at all. And here's my rational, possibly apocryphal reconstruction of what I think happened. It seems that Turing's mathematical model was so interesting in its own right that it was taken to be the foundation of computation. It's what we've all focused on, right? And let me make a maybe not perfect, but again, kind of an analogy with, like, say, differential equations. So differential equations, they're physically useful. They were developed to study physical systems, right? They're also mathematically interesting just in their own right. Not every mathematician who studies differential equations wants to apply it to something, right? But it would be a mistake to confuse the equations for the physical systems that they describe, right? And moreover, it would be a mistake to think that systems are of a certain kind only if they implement those equations, right? Lots of systems can be described by those equations, but it seems weird to talk about physical systems implementing differential equations, right? And further still, it would be a mistake to think that every differential equation that you can come up with must describe some possible physical system or other. Right? And this is one of the things, I'm sad to say that Gualtiero's not here. One of Gualtiero's motivations for this idea that computation can be divorced from representation, he says, look, there's lots of these automata out there that do things and they're not representing anything. And those are computations, right? Well, okay, you could insist that every possible differential equation must describe some kind of physical system or other, right? And I think we're making a similar mistake here. Yes, those things exist mathematically and they're very interesting to study for all sorts of reasons, right? But they don't all describe computations. So what is necessary then? Let me wave my hands a little bit. Representations that can be manipulated. That's what the Antikythera mechanism has. That's what slide rules have. That's what digital computers have, calculators, all of the really clear examples of computers that we have. They start with representations and they can be manipulated. The manipulations that can be done are of the properties that are doing the representing, right? So a slide rule, or say just a meter stick, whatever, has a temperature, you know, it has a mass, has all kinds of things. If it's the length that's doing the representing, if that's the relevant magnitude, then that must be the property that's being manipulated by a computational system, right? If it's a digital system, it's however the digits are being implemented physically, right, with respect to those properties. Right? I can say more about this. I'm trying to just paint a picture. And then for computational mechanisms, which I think is what we really want to get a grip on, the manipulation has to be performed by a mechanism in a kind of robust sense of mechanism, not just any old mechanism, but a mechanism that's sensitive to those properties and has other features of mechanisms that everyone likes to talk about these days. So I think this gestures toward a representational account of computation, which has the most in common with actually Chagrir's semantic account of computation, but comes from a different starting point. And I would argue that this captures all kinds of computation that, you know, we've called computation this whole time, and it rules out non-computational things. And I've argued elsewhere that this applies to both artificial and natural systems in kind of a testable way. Like, do you want to know if this part of the brain is computing? Well, answer the question, does it have representations? Okay. Are those representations manipulated such that whatever the properties of the representations are that are doing the representing, those are the properties that are being manipulated, right? Fundamentally, right? By some kind of mechanism, right? If you don't have those, then you don't have a principled reason for saying it's really a computing system, right? Metaphorically, you can do what you want, but I think this is a way to get at what's literally a computing system. And I've argued that this is actually what a lot of neuroscientists who take seriously the idea that brains compute have in mind. This is like what's going on in the background of when they say seriously, you know, this part of the brain is computing or whatever, right? And then it also helps us to make sense of, you know, these various other ways or places we might want to say something is computing or not. DNA computing, perhaps quantum computing, computing with Fizarium, slime molds, right? Is it just that we're describing what they do in terms that could be mapped onto an automata? And so we're saying, yeah, it has this kinematics, you know, and maybe it's discrete states, maybe it's continuous, whatever. Great, lots and lots of things can do that. But what's interesting about computation, above and beyond just capturing kinematics, is the manipulation of representations, right? Yeah, the details would be made more precise. Happy to talk about more of those, but that's for another time. So that's it for now. Thank you for your attention.
Okay, so. Yeah, I'm doing.
Super cool. Thank you. I guess I was curious about what you said about how in these analog cases, there's no implementation of automata. And I guess, I mean, sort of one, maybe this question is too big, is like sort of, one thing I'm curious is like what goes wrong in those sorts of cases. I want to hear a little more about.
Sorry, can you speak up a little bit?
Sorry. So when you say that there's no implementation of automata in some of these analog cases, sort of, I guess I have a couple of questions. One is just like, I want to hear more about what goes wrong when you try to spell things out in terms of implementation. Maybe that's too big of a question though. So I guess I'm curious where you think it sort of leaves us, or where we should be. Yeah, where we're left with implementation talk. And I guess I could sort of see there being a stronger and a weaker version. The weaker version, I guess, would be like maybe implementation talk is okay in some cases, like digital computation. But then what you said right at the end suggested something stronger, which is maybe that you're advocating a break with thinking about implementation more generally, and we should move in this more sort of representationally based direction. So yeah, I guess, where are we left with respect to implementation on the picture that you have?
Yeah, so as to the first point, if you think about either of those devices that I showed you, right? Neither of those they correspond to automata in any ordinary sense.
Yeah.
Why? Well, because I mean, setting aside that they're not discrete, they could have been discrete, sure. But the way that the variables are manipulated, I mean, that's just outside the scope of automata theory, right? And some people in computer science will say, well, look, you could approximate those as close as you want. Sure, that's not the point, right? Those things just are not implementations of automata, right? Maybe you can cook up something that's automata-like in the right sense, but then the tricky part becomes, and this is something I've argued in print, one of the supposed benefits of being able to implement automata is some degree of medium independence, right? The problem with those mechanisms that I showed you is that they're not medium independent in the same way that digital computers are. Why? Because in a digital computer, right? Take a simple example. So you have some, you want to represent some bits in binary, right? What do you need? You need some discrete states that can be, and each one of those can be in a couple states, right? Okay, so you could do that with water temperatures that are in different, bistable things, or voltages, or colors, whatever you want, right? The physical properties themselves don't really matter. It's just that the physical properties are being understood as digits, right? Whereas in that mechanism with the integrator, it's essential that we can talk about length, right? And we can talk about rotation. Now, there is a sense which we could have made that device with wood or with steel or titanium, right? They're multiply realizable in a sense, but the representations, what's doing the representing is a physical property, not an abstraction from a physical property to a digit, right? So the implementation becomes, I can't see a reason to call it implementation at all, right? The second part, yeah, there might still be a room for implementation when we're talking about systems that we design, or digital systems more generally, or whatever. But I mean, for me, one of the big things is to say, well, let me just say a larger point. If we're going to really worry about whether natural systems are computers or not, first of all, maybe they're analog, maybe they're digital, maybe there's another kind, right, that I haven't talked about yet, right? But we don't need to say, well, look, if it's a computational system, then we got to look for the implementation. Well, maybe that's not a necessary component, right? It's got to be medium independent, maybe not, right? And then you can say, well, wait a minute, then what makes it computational? The same thing that also makes analog computers computational, right? I want to say, here's a general story of computation, and then there are species of computations that have their own properties, right? But the general thing that makes anything computational is what made the Antikythera computational, and slide rules, and abacuses, and pocket calculators, right? So that's the kind of idea. Maybe there is a room for implementation, but it's not necessary. Is that okay? Cool. Thank you.
Okay, I have to say, I think it's, I was really interested in this. I'm a bit confused, I have to admit. I don't necessarily get entirely what is an analog computer in your view. So just maybe for clarification, a question. Take this simple device that's used in Montessori schools with marbles and balls, where you can do actually very simple but also quite complex computations in a way. Is that an analog computer?
I mean, it's an analog computer insofar as, so the simple counting devices that people use to count, like people in a queue or something, where you push a button and it advances a little counter.
Yes.
Right. If that counts as a computer, then so does, I put a marble in the bowl every time a person goes through the line.
Well, it can do quite, it can do quite large numbers, so one bowl represents 10s, 100s, and
Oh, sure.
so you
Yeah.
can do this, so that's analog.
Yeah. I mean, so analog computing, digital computing, any kind of computing is gonna have the same problem, like where do you draw the line where it's so simple that you don't really want to call it computing anymore? Right? The analog computing, all it means is what is doing the representing is the magnitude. Yeah, and so if it's, you know, you put marbles in the
It's
jar.
one of both. I mean, the marbles have a magnitude, I mean, they have a size and, you know, and then some.
Yeah.
The size or, you know, represents a one, but at the same time, they represent numbers and then sometimes a marble represents hundreds and sometimes thousands.
Oh, sure, so.
It seems to have both, sort of. You know.
Yeah, I mean, so there. Maybe I'm not understanding the example, but you could say like, okay, the blue marbles stand for one person, the red marbles stand for 10 people, the hundreds, the green, whatever, right? Then it sounds like what you're doing is implementing digits with colors of marbles, right? Instead of symbols, right? If what you mean is, it's something like,
It actually, in which bowl they are, they tend to represent something that's.
oh yeah, then that's just gonna be like a weird digital representation, right? Like here's the ones place, here's the tens place, here's the hundreds place, here's the thousands place. It's a weird kind of case, but it's like each digit, instead of being represented by a symbol, is represented analogically. I had a clock that was like this, right? Where instead of a symbol for the ones, it's how many lights are lit up, like a little bar graph, right? Instead of a symbol for the tens place, it's how many lights are lit up, like a bar graph. So each digit is being represented like it's an analog thing, but it's not like you just add them all up and that's the quantity.
But they would be analog in your view if the marbles represent, if the marble size would be, or the. It would be used for simple adding to something, for instance.
Yeah, if the
Then it would be
size,
analog.
and it would also be analog, this is how many marbles there are, right? I'll take count as a simple analog representation. Yeah,
Okay. I think more about this, I guess.
I mean, you know, another example is, it's like the hourglass thing, right? Say that the beads in the hourglass are large enough that you can like count them. Yeah, so it's like, it's a discrete yet analog representation. How many are in there? The number of things in there is the number of whatever the units are that have elapsed.
Yeah, kind of our hearts beat as one on this.
Oh, good.
Three kind of observations, I don't
Okay.
know the really question. The non-dissignature, you said that his account was kind of so interesting that somehow we got addicted to it and forgot about analog. We regarded it as an analysis of computation in general. There's another way of describing it. Turing wanted to analyze digital computation and did so. He did so at a time when analog was fading and digital was growing. And that's the explanation of the fastening on his account.
I don't agree with that.
Confusion.
I don't agree with that because the 40s, 50s, and 60s were the heyday of analog computers. I mean, they were, when you went to buy a computer, that's what it was. And then when the digital computers came on the scene, then they had to start distinguishing the old ones from the new ones. And that's when the digital and analog distinction came about. And people didn't even like the digital ones at first because they were too slow and not even as accurate as the analog ones. Right?
Yes, well, that's true. But people were talking about digital computers to distinguish them from analog computers.
Right,
In
exactly.
the mid-1940s. And the people who were keen on digital computers knew that analog was as they thought, you know, kind of yesterday's technology. And there was von Neumann proving his results about, you know, how do you get extra precision? Well, with a digital machine, it's easy, with an analog machine, forget it,
Right.
you keep in extra hardware. And there was the speed and universality of digital machines.
Right.
So I think there were kind of, to cartoon it a bit, there were kind of two groups of people back in those days. There were the people who'd seen the digital light, and they took on computer
Yeah.
numbers as the analysis of digital computation, no confusion. And then there were the people who kind of saw that there was still some future in analog computation, particularly commercially, you know, all
Right.
sorts of applications. I don't see any scope for the kind of the confusion that you're suggesting.
Well, okay, so the confusion, maybe I should put it in this way. People in the philosophy of mind started talking about maybe the mind is a computer. Was the only thing they had in mind? Turing machines.
Yeah, that's probably true. But
Yeah.
philosophers, yes, the technologists, no.
Yeah, so the other thing that I want to do here is have some kind of unified account of computation that like everybody can get on board with, that unifies all these things in some way that's principled. And so the people who are, people like you would be like, oh yeah, that sounds right. That does justice to history, right? Yeah, so there were definitely people who were not confused about this. There were other ones who really were confused about this, right? And so I'm speaking to not the people who were confused, but a lot of those people are dead now too. So, yeah, but yeah, I take your point. Yeah.
Kind of this is an observation that I kind of guess you might have made, but you didn't, but it's sort of all grist to the mill. Back in the the transitional days when analog was there and digital was emerging, they would actually use the same circuitry to implement both kinds
Yeah,
of things. They have a single device which could be used to represent in an analog way. So you have lines on a cathode ray tube that would
Right.
represent the magnitude of the object, the distance of the way of objects.
Right.
Or equally, using the same technology, you could have a sequence of bits on that same screen.
Mhm.
Be a digital representation of a number or something.
Yeah, and maybe this is worth making even clearer what the difference was there in this when the electronic analog computers and the digital computers were coming on the scene. The people who wrote a lot about this were computer engineers, so they're not trying to get in all the philosophical details, but it's especially in the case of discrete analog computers, one of the differences was, for a digital computer, 0 volts roughly and 5 volts. 0 volts means a 0, 5 volts means a 1. And a whole sequence of those things is a digital representation of a number. Whereas in an analog computer, you might have a circuit element that can only go in discrete steps. So it'd be 0 volts, 1 volt, 2 volts, 3 volts, 4 volts. And the value of the number being represented was just the number of volts. So if you wanted 16 volts, you just have a circuit that's at 16 volts, right? And so that's another way of just kind of piggybacking what you said to illustrate, this is a fundamental difference between digital and analog. It's not just discrete versus continuous. It's, are you taking those voltages to be representations of digits, and then the sequence of digits is the number you're interested in? Or are you taking the magnitude of that value just to be the magnitude of the number that you're interested in, right? And yeah, they could use some of the same components depending on how they wanted to use them in the system.
Yeah, it
good.
seems to me to greatly strengthen the kind of principle you're arguing for. They did use exactly the same electronics to do both kinds of representation.
Yeah.
On the same screen.
Yeah, good. Thank you.
I've got a few more bits, but I'll put these on the time later.
Owen? Yeah, thank you. It was really interesting and yeah, of course, I agree with most of the things. One thing that maybe we even corresponded a bit about this is about it's not that I have an answer, but it's about the magnitudes, okay, what we call the physical magnitude, because the physical magnitudes in a way are also some kind of mathematical schemes that we impose on the physical system. So for instance, if you use temperature, for instance, to compute, so if you impose Fahrenheit and you impose Celsius, correct, the same system might do different things because in a way the magnitudes become different. And maybe the flip side is the example you gave, the first one in the multiplier. So you gave the multiplier and then you put labels, the numbers or things like this, and you say that now we can see how it multiplies. But of course, I think that those numbers have nothing to do with the computation. It is something
Yeah.
that is convenience for us, and in a way also not the physical things there. I mean, what is really important is multiplication is defined by certain relations, that it's symmetric, it's associative, there is the zero thing, and the distinctively define the function. And this system that you showed simply satisfies those conditions, and this is why it is a multiplier that we impose. And by the way, it's not necessarily the case with lookup tables like slide rules. I mean, there, if you do multiplication or something, yeah, well, maybe I leave this aside. It's another complication.
Sure. Yeah, so you're right. So one simple thing is, for example, in the electronic analog computers, say you wanted to do something having to do with, I took some NASA archives about the analog computers used to, in the Apollo program. And you can't run 250,000 volts through your analog computer, right? So you have to linearly scale everything down, right? Okay. That's not a problem, right? It's just everything is just linearly scaled down, right? I mean, as a practical matter, sometimes it was a problem of like, how exactly are you going to do this so everything is within range and you don't start your computer on fire? The trickier and more subtle point is, yeah, this is something that I'm only beginning to get into and understand. Only certain types of magnitudes are going to be able to do the jobs that we want. And of course, there is a way in which we're imposing something on those labels, right? But there are things in, for example, measurement theory, right? So things are, I'm probably going to get this wrong, but there are certain, I guess, axioms of measurement theory that are going to have to apply to the magnitudes in order to do the things that you want them to do, right? So length, for example, will work for addition because length has all the properties that addition does, right? Voltage in some cases will do the job and in other cases not, right? And so there is a principled way to say, look to measurement theory to put some constraints on what kinds of physical magnitudes are going to do the job that you want, right? And if you want to say, but even that's arbitrary, like, okay. And it's also true if you wanted to, you can do the thing where you can say, I don't care about lengths. I'm just going to randomly put numbers on there and put random numbers over here. And then, this will compute some wacky function. But okay, so now you're not using magnitudes anymore, right? I take it that magnitudes are real things in the world. We do have to label them for convenience. And for them to work as magnitudes, we have to use these axioms of measurement theory. But again, I'm getting beyond what I fully understand, but that's where I'm looking to in principle sort of answer. Thanks. Yeah.
This is kind of a follow-up of that. I like what you're trying to do. I'm very sympathetic, but I do see that what you might call the readout problem. So thinking about your multiplier, the scales are different, right? A and B seem to be the same scale, but C, the output has to be, and it's the same thing with the logarithmic scale and the slide rule, et cetera, et cetera.
Right.
So ultimately, you're right that the manipulation is of magnitudes, but the readout, the part that actually makes it a representation, still has this discrete, and even if you didn't have numbers, you have to have little marks in there. It still has this discrete element. So it doesn't seem like they escape discreteness.
I'm fine with that.
Brain, which does a bunch of continuous stuff, ultimately it's firing action.
Yeah.
So does this kind of discreteness, is it intrinsic to computation? Because it seems by your arguments, it could well be. Discreteness, without discreteness, you can't do it. You can't do it usefully.
Here's the thing, I mean, like the kind of metaphysical, philosophical point I want to say is that I don't want analog representation or digital representation to stand or fall with whether there really is discreteness or really is continuity in the universe in some deep sense, right? That's why I say, you know, I don't really care if analog representations are truly continuous or discrete. That's not the important point, right? And if it turns out there is no continuity, that's fine. There still is a difference between representing things digitally and representing them in analog magnitudes. It just turns out those magnitudes happen to be discrete. And neural firing is actually an example I've used in one of my early papers, right? To say, look, maybe analog computation is a better model of computation for neurons. And a really simple example, right? Like Adrian's old experiments with like, you know, muscle cell, right? Increase the mass, stretching the cell, and you get an increase in the firing rate of the neuron, right? Is firing rate a continuous variable or is it discrete spikes? I don't care, right? What matters is you have one magnitude mass being represented by another magnitude, increase in firing rate, right? That's analog. It's not digital because there is no digits of numbers that are being represented anywhere, right? And lots of simple, I'm sure you know, lots of examples in neuroscience are like that, where generally, as you increase or decrease a stimulus, you increase or decrease, you know, firing rate in this like monotonic way, which I said that just is analog representation. And if it's monotonic like this in steps, or you know, one's continuous and the other one is in steps, whatever, it's analog. Yeah. And that is most people think analog equals continuous, right?
No, I agree.
Yeah. I'm saying that's all right.
Yeah, my question.
Hi.
Hey, so I have first a quick remark. So I really like Pi, and I've been investigating histories, and there's a very nice foundation as Hubert. You can check. There was this guy in the 17th century studying properties of Pi, and his name was Rudolf or something.
Mhm.
Dutch, I think. And for this reason, Pi is also called Rudolf.
Okay.
No,
Good to
we'll
know.
have another name. I really
Sure.
like this one. Good. So, well, I read your paper recently, and now I was listening to you, and there's like a detail that I am still missing, right? And if you would have something more to say, I would be grateful. So, I understand perfectly how digital representations differ from analog representations. And that's easy, right? I mean, that's easy for me. But I have a problem understanding analog computing process because you're using a lot of expressions step by step. And this is what I'm thinking is more related to, yeah, maybe this is what you said, that continuous, that analog does not have to be necessarily continuous, right?
Right.
But I can imagine that there is analog and continuous, right? So
For sure.
like our intuitions are not wrong. So what would be this continuous process? Are they, because in your paper you say that in order to have this analog computation, we have analog representations, but then computing goes as usual with a discrete process,
I mean,
right?
it can be discrete. It doesn't need to be at all.
But could you describe for me a process which is like clearly continuous on continuous representations? Because I have hard time to imagine one, and maybe it's just constraints of my imagination and lack of experience. But if you
Sure.
can help me, I would be very grateful.
Sadly, I don't have a picture in these slides, but in electronic analog computers, one of the main components was an operational amplifier, an op-amp, which is the way that you integrate signals, right? And the signals, these were usually used to model just systems of differential equations. And so the signal coming in was continuous. All the electrical signals were continuous. What it did was continuous. It's, I mean, as continuous as you think that electrical signals can be, right? Or, you know, if you want to think of in the integrator that I showed you,
Yeah.
think of that movement as continuous.
Yeah.
Think of the rolling as continuous. right? Everything there was continuous.
I have to think about it more because I necessarily always end up on the discrete process of this, like in a description, I always end up in the discrete process. And maybe it's, as I said, just lack of my experience in the area of analog and continuous. Okay, thank you.
Right, so I think we have a question from Diane. Yeah, Zoom. No? Okay, so, yeah, Orly?
You mentioned very briefly that in analog computations, there is no distinction or no clear distinction in hardware and software. They go together. And that's the case also in contemporary quantum computation.
Mhm.
But I'm curious about, standard digital computation, because it seems to me that even there, if you look closely at what's happening there is no distinction hardware software. I mean, the
Yeah.
software is just the thing about these devices is that changing the circuit is very easy. They're flexible. So we just change the hardware all the time and we call it software, but there is no real distinction out there.
Yeah, I mean, that's a really good point. And this is a tricky issue in like the ontology of software, right?
Yeah.
Because we talk all the time about these sort of abstractions from the hardware and what, like those aren't really faces, those are, pixel values, right? And it's creepy, I can like see myself on the screen, but like that image of me is not really moving left to right. What's happening is a bunch of pixel values are changing, right? Yeah, so in some, very reductionist sense, yeah, it's all circuitry, right? And you learn this intimately when you take a compiler construction class in computer science. So if really pressed, yeah, I'd have to say, okay, if you want to take seriously that there really isn't software, okay, right? That's going to be a hard thing to sell. I don't know how many people are going to buy it because you can say, well, okay, what I mean by software is that in certain elements of those parts of the system, sometimes the voltage changes that represent digits are interpreted as instructions to make the machine do other things. Sometimes they're interpreted as data that are operated by those instructions, right? That seems like a really helpful abstraction to have. And when you just look at, if you just look at the circuitry, you can't make that distinction, right? It's all high and low voltages, right? And if you just look at what they're doing, you really can't do that either, right? You have to abstract from that to even get a grip on, oh, those ones are the data, those are the ones with the instructions, right? And that's the level at which software, I don't like the word emerges, but software appears or it's abstracted, whatever. So insofar as that's a thing, analog computers don't have that, right? So I think that's a great point. And it's one of these things that I wish more people in the philosophy of computation would take seriously. Like, how do we really understand software? Because I mean, my philosophical tastes are like, yeah, you're right. Like it's not really there. But then everyone's gonna be like, okay, so what are viruses then? Like what's Adobe Photoshop, right? It's not a bunch of circuits, so yeah.
Thanks. So thanks for the talk, of course, and
Yeah.
I really enjoying your approach and getting up on them. And we all know you almost always gonna be up about 9% of and stuff, but the last 10%. But anyway, I think main points for time. So just to jump on what Nate said before, because I think I agree in the sense of. So I'm trying to understand exactly where you draw the line. The main point. Because if you say, okay, analog is whenever we have like representations of quantities, numbers with physical quantities.
Well, representing the magnitudes of numbers by physical magnitudes,
Right.
or quantities. Quantities are interchangeable there. Yeah.
Yeah, I feel that it doesn't capture, I mean, we would only intuitively say that the abacus is digital,
That's sorry, the what?
that the abacus
Mhm.
is a digital. Divide,
Maybe.
that's a strong intuition, but then it does exactly what you say.
Mhm.
Somehow it's as James said, it's magnitude.
Mhm.
We represent there. So I think that's it, that could be a counterintuitive aspect of the account, but an abacus
Possibly.
analog. The other thing is that, if I understand you correctly, you would say that, a watch, an analog watch is analog because somehow the physical magnitudes, the angles,
Angles, yeah.
these things that we represent the hour, the passage of time by angles. But then again, Babbage's machine or machines based on years,
Mhm.
which we would intuitively again say that Babbage's machine was digital.
Mhm.
There, you represent the numbers by angles of the years. Like if you look at a picture of some year in Babbage's machine, you will see that here is 10, 9, 8, 7.
Right.
So it's specific to specific position. But then we read this as digital again.
Okay. Can I respond?
Yes, yours.
Okay. Let me take the Babbage thing first. So the Babbage, if I'm remembering the right way, the way that Babbage represented numbers, it's like the old school odometers in cars, right? Where, you've got this digital representation, but the numbers are on like wheels, spin, right? I'd say, yep, that's a digital representation. Like there's a wheel that goes, to get from 1 to 2, it rotates, to get from 2 to 3, it rotates, etc. And then when it's 9 to 0, then it makes the next one rotate, right? Yeah, that's digital. Why? Because if you're representing 10,000 miles, you've got a 1 and a 0 and a 0 and a 0 and a 0. It's not the there are angles involved, but it's not the angles that are doing the representing, right?
Because it's positional, you say, because it represents the positional system, the
Yeah.
positional,
Right.
the positional feature of the decimal system we're using.
Mhm.
Let's say just 1 from 1 to 10. Let's say we want to do computations from 0 to 10.
Uh-huh.
Why is this physical?
Well, okay, so yeah, so they're going to be,
Even that the clock, the watch for you is the analog, right? Even that you would read the analog versus analog because it's again positional.
yeah, these are cases that I think can be really misleading because most analog watches, some analog watches have nothing, it's hands, right? You just have to rely on the angle. But sometimes there are numbers like this one. Look, here's a digital representation of 11, right? Does that make it a digital clock? No. Why? Because it's the angle that's doing the representing. That's kind of convenient to have, so you can like get a little more precision, right? But it's still, that didn't turn it into a digital clock. Also, if these things tick discretely, that also doesn't make it a digital clock, right? Right. This, I paid attention. This does seem to move continuously, very slowly, right? But some wristwatches tick with the seconds. For the abacus, yeah, there's this deeply held idea that discrete equals digital. This is like, as you say, this is like this intuitive thing you want to say. Okay, I mean, we can say what we want, but I've given a reason to say, it's not digital just because it's discrete. I have an argument for this, right? Why? Because you're representing magnitudes with magnitudes, right? And this happens with doing philosophy all the time, right? Sometimes you're going to say like, yeah, these cases that you intuitively thought were one thing, they're not on my theory. We do a little reflective equilibrium. Do you want to stomp your feet and say, no, this is a data point that I'm certain about, that means your theory is wrong? Or do you want to say, this theory, your account is like, I buy that. So maybe this data point is, my intuitions are wrong, right? I mean, it's a decision to make. I would just say, look, separate discrete from digital and your problems go away.
Right. One last quick question, very quick. I enjoy the whole things. Does your account require representations beyond that of numbers? Those abstract entities that don't exist, maybe?
Yeah, so this is like one of the things that I wish Okay, so as we all know, right, in digital computers, way down at the base level, there's, you know, voltages doing this, they're waving their hands, right? To understand it as a computational system, you have to get like, oh, well, those actually represent digits. The digits, you know, are in strings that represent numbers, and that's important. You know, when you're doing computer engineering, there's big endian and little endian. It's like, is this side the most significant digit, or is this side the most significant digit, right? It's not just that it's discrete, it's really numbers, but sometimes those numbers represent instructions, sometimes they represent data, and that data can represent pixel values and all sorts of other things, right? So yes, you can kind of build abstract layers where the representations aren't just of numbers anymore, right? But digital computing system, quad digital computing system, it's all numbers, right? And that's really convenient. I mean, there are really good reasons for doing that, right? That's another tricky issue in the metaphysics of software and things like that, right? I mean, obviously, this is not a representation of a number, right? It's right? It's somewhere in the circuit, right? But at base, yeah, it's representations of numbers. But this is one of the things too, where I want to say, okay, what if there is some principled way of saying there is computation and it's not at its core representations of numbers, right? That's what the anti-theorem mechanism did and Slide was and all that, but like, maybe there is a useful way of thinking about computation. It's not at its core representations of numbers. Cool. Let's start with what we know are computations, right? And hopefully you brought like some principled ways and see if that has anything to do with this other stuff, right? Maybe it doesn't, maybe it does. I don't know. Just, you know, we'll see.
Okay, so thank you very much.